Okay. So yesterday we spoke about mass balance and energy balance. And under the energy balance, we specifically looked at the mechanical energy balance. And that's what led us to the Bernoulli equation. But when we were looking at the Bernoulli equation, we made some assumptions. So we assumed that there was no friction. That's the an ideal fluid. And then we assumed that there was also no shaft work. So our expression was simplified. But we want the equation in a way that we can account for frictional losses and then work from pumps as well. Because that's what happens in reality, right? So we are not dealing with an ideal case. Once you look at what happens in a real situation, we first start by looking at fluid friction. So when we have any real flow of fluid, as we said before, viscosity will tend to resist the flow. And so there's going to be a transfer of momentum to the wall of the channel. So we spoke about this in our very first discussion when we looked at um, the flow of fluids and the fact that the viscosity is going to retard the flow. And this is going to cause momentum to be transferred, right? Now, the work that is going to be done by the shear forces in maintaining these velocity gradients is eventually converted into heat by viscous action. And then this heat is absorbed by the fluid itself. So what we are just trying to see over here is that when the fluid is fluid, the shear forces within the fluid that are causing the velocity gradients to be formed, right? These forces would eventually be converted into heat. Is that okay? Or the energy within them is going to be converted into heat. And then we use this example the last time when we were speaking about is that if you are walking, there's friction between your footwear and then the ground. And then that friction is going to generate some kind of heat, right? So the mechanical energy that you are putting in is going to be transformed to some form of heat because of the friction around. So fluid friction can also be defined as any conversion of mechanical energy into heat in a flowing stream. And because of this energy conversion, we can call friction loss friction heating. So another name we can give to friction loss is friction heating. This is just something for us to take note of. Now, energy converted to heat is lost work. So what we know is that if I have an amount of energy, right, and I'm using it for something, the energy that gets lost usually in the form of heat in the system that we are dealing with, right? So friction will manifest itself by the disappearance or the dissipation of mechanical energy, and then that energy will change to heat. Now, because there's energy being lost, right, and it's going to, and there's energy that's being lost. So we are going to consider this at the output. We are going to consider the effect on the output, right? So we introduce our friction factor or our friction term at the part of the Bernoulli equation that represents the output, but it's going to be less than the part that represents the input. This is what I'm trying to say. If I have a certain system, there's an input and then there's an output. But because of friction, what is coming out is going to be less. So it means that what is coming out plus something, right? Let's say that's going to be our H, is going to equal to what is coming in. That's what we are just trying to say. So that's going to be our I. So out plus our friction is going to be equal to our input. So we add the friction and the fluid friction term to the output side, right? Then we can also, so yes, the corrected, and this corrected by adding a term HF. So HF is going to represent our fluid friction term, right? And if you want it in the head form, divided by the acceleration due to gravity constant. So we spoke about that the last time that we can have the Bernoulli equation in the raw original form, or we can have it in the head form where we divide by acceleration due to gravity. Is that okay? So we can have HF to be our fluid friction term, then HF over G would be the fluid friction term in head form. Okay, so this term represents all the friction that is generated per unit mass of fluid. And it also represents the conversion of mechanical energy into heat. That occurs in the fluid between station one and station two. So remember we had a certain diagram. It was a conduit, a channel, a pipe, right? It looked something like this. And it became a bit narrow. So it was something like this. And then this was station one, this was point one, and then this was point two. So I'm just saying that there's some form of mechanical energy that's going to be converted into heat as the fluid is moving from station one to station two, right? So the energy that's going to be converted into heat from one point to the other. Okay. So before I go on, is there anything I should go over? Please, can I be here? Okay, my line is breaking. I'm coming. Okay. Um, can everyone else hear me? Can everyone else hear me? Okay. So someone said they can hear. So I think Amanda, it might be from your end. Sure, then let's carry on. So all we are saying is that in our system, right, in a real system, we need to account for the energy that's going to be lost because of friction. And we add that to the output side of our equation. So that term is our HF. In the head form, it becomes HF over G. Just when we said that the head form is just the equation in its original form, and then we are dividing every term by acceleration due to gravity. Okay. So this was our equation, our Bernoulli equation in the head form, because everything is divided by gravity. Remember that the z was multiplied by g. So if I divide by g, then it cancels out. So this was our equation in the head form. And everything at point two is the outlet, right? So we add our friction, our fluid friction term to the outlet side of the equation. So our HF is our friction loss in joule per kilogram. And then the mechanical energy balance, if we should send everything to one side of the equal to sign, we can simplify it into this form, right? Now we realize that we see a certain WS here. This WS is also going to represent shaft work or work that will come from the pump. Is that okay? So we are introducing both the friction term and then the shaft work term. So we'll talk about the work very soon. Okay. So when we do not cancel out shaft work, or when shaft work is present, then this becomes the general form that we work with. Right. So what you can do is that when you are given a question, you can start out with the general form and then you cancel your terms as you go on. So if you assume that there's no shaft work, you can cancel that term. If you assume there's no fluid friction effect, you can cancel out this term as well. Okay. Now let's look at the shaft work that we can get because of the presence of the pump. When we consider a pump is used in the flow system to increase the mechanical energy of the flowing fluid. And then the increase is used to maintain the flow of the fluid. So the value of our friction and our fluid friction effects will depend on the detailed nature of the flow. What we are trying to say is that the frictional loss that we are going to get, it depends on the properties, the characteristics of our flow. So the properties of the fluid, the properties of the material the fluid is flowing through. These things would affect the frictional effects, right? And we can determine these things for theory for flow through conduits or pipes. But then we can't do this when we are dealing with pumps. So what they're trying to say is that we can find HF when we are looking at pipes, when we are looking at channels that fluid flows through. But when we are doing it for pumps, it becomes difficult. You can't easily find HF for pumps, the friction effects in pumps, right? So friction occurring within a pump is due to not just the fluid friction, but the mechanical friction as well. That's why it's a bit difficult to determine it from just theory or from just calculations, right? So the mechanical energy that we give to the pump as negative shaft work must be discounted by these frictional losses to give the net mechanical energy actually available to the flowing fluid. So what we are saying is that when we input some amount of energy to the pump, the amount of energy that the pump is actually able to use is less than what we put in because it's not going to be 100% efficient. So what I'm trying to say is that when we put in, let's say, 100 joules of energy, right, into our pump for our pump to work, there's going to be some effects, effects from the frictional losses in the pump and the mechanical friction as well in the pump. When that happens, instead of you getting 100 joules of energy coming out, you might get about 94 or something of that sort. right? So that's what we are trying to say. So the amount of energy the pump is actually able to input into our fluid stream is less than what we are actually supplying to the pump. So that's where we have the pump efficiency coming in, and we represent it with this symbol. So this was supposed to be a subscript P, right? Represent the efficiency of the pump. So for pumps, we use the efficiency of the pump instead of using the frictional effect in the pump. And we know that the expression for efficiency is the useful amount of energy over the total amount of energy. The useful energy is the total energy minus what was lost because of the friction effect. Just as we said, I can input 100 joules, but then because of friction and mechanical, and because of fluid and mechanical friction, I might get just 94 joules coming out. So I take the total amount of energy minus what was lost or what went to waste, right? That becomes the amount that I actually used divided by the total amount I put in initially. That will give me the efficiency of the pump. Now, remember we said that this over here, the total minus what was lost becomes what we are putting into the system, into the fluid. Is that okay? So I spoke about that in the last point here, that the WP minus HF is the energy delivered to the fluid by the pump, and that becomes the shaft work expression, right? So the shaft work is negative for pump because the pump is acting on the fluid. And remember, for the convention we use in fluid transport, when work is done on the fluid, it is negative. Now we are saying here that the efficiency is always less than 1 or less than 100%, right? We can't have something to be 100% efficient for our pumps. And then WP is just the energy supplied to the pump in joule per kilogram, right? So all we are just trying to say now is that a useful energy over total energy, we can represent it with this expression. And we said that WP minus the HF is going to be the amount of work that the pump is actually going to do on the fluid. So that will be the shaft work. Is that okay? And we said the shaft work is going to be negative because it is being done on the fluid. So we can just see that our efficiencies are minus WS over WP. Now we can make minus WS a subject and we have NP times WP, right? And if we want it in the head form, we divide by acceleration due to gravity. So we have that expression. So we can have the Bernoulli equation where we include both the fluid friction and then the pump work. So a minute. Okay, sorry about that. So we have the original expression here. So all the things at the outlet, right? Remember we said we add the fluid friction term to the outlet. The work coming from the pump, because it is work that is being done on the fluid, is going to give energy to the fluid. It will come in the inlet term. So we see point one was our inlet, point two was our outlet. At the outlet side, we add the fluid friction term, right? Because it's going to reduce the output. At the inlet side, we add um the work term coming from the pump. So please just take note of the expression. Is that okay? Now we have an example here. We have water with a density of 998 kilogram per meter cube flowing at a steady mass flow rate through a uniform diameter pipe. Uniform diameter pipe means that the diameter of the pipe is not going to change at any point. Right? So unlike the case where we had the pipe looking like this and then it became a bit narrow. The pipe was like this and became a bit narrow. What we are saying right now is that it's just going to be the same diameter throughout. So that's the uniform diameter pipe we are talking about. Now the entrance pressure of the fluid, we're told is 68.9 kilonewton per meter squared. It's absolute. So that's absolute pressure in the pipe. And it connects to a pump that actually supplies 155.4 joule per kilogram of fluid flowing in the pipe. So they give us the inlet pressure and then they give us the work that the pump is doing. Now the exit pipe from the pump is the same diameter as the inlet pipe. So we already concluded on that. And the exit section of the pipe is 3.05 meters higher than the entrance. Then they give us the exit pressure as well. Now, one thing to notice, if you are given your pressure, realize that this was given to you as absolute pressure. If this was given to you as gauge pressure, you have to make sure that they are consistent before you carry on with the calculation. Now, the Reynolds number in the pipe is above 4,000 in the system. I'm being told to calculate the frictional loss in the pipe system. So this is the question once again. We can draw a diagram. So we have our pump, and this is the work that the pump is doing. We have our inlet, and we have the conditions at the inlet. So the pressure at the inlet was 68.9 kilonewton per meter squared. We don't know the velocity at the inlet. And then for the height and the inlet, we're taking this to be our reference height. So we are starting from that point. So that becomes our point zero. Then we can have the outlet. So we have the pressure at the outlet. We also don't know the velocity at the outlet. But then we know that Z2 is 3.05 meters from Z1. So if we're taking Z1 to be 0, then Z2 will be 3.05 meters. Now the question gave us the Reynolds number, and that just indicates that we have turbulence flow. If we look at the value, we have turbulence flow under ordinary conditions. The reason why they mention this is because we assume turbulence flow when we are dealing with the Bernoulli equations. One of the assumptions we make. So we looked at that yesterday when we were looking at the Bernoulli equation, that we can assume turbulence flow for our calculation purposes. If we do not assume turbulence flow, it would affect the velocity term with the expression. But I think for that one, it's not something you have to worry about for now. Okay, so we assume turbulence flow before we can use the Bernoulli equation as we've seen it. Now, the part of the question that's mentioned the Reynolds number was just to support that assumption that we are actually dealing with turbulence flow. So we can use the equation as we know. Now, the question also mentioned that the diameters of the inlet and the outlet pipes were the same. So remember this expression, the continuity equation, when we're looking at mass balance. We said that rho VA would be constant through the pipe. So as the inlet, it should be equal to the outlet. But we know that the question said we are dealing with a constant density. So the rho can cancel out. And then the diameters are also the same. So the areas can cancel out. If the diameters are the same, the cross-sectional areas will be the same. So they can cancel out. And then all we have left is V1 is equal to V2. So once again, we have our question here, a diagram. And this is our Bernoulli equation with our friction term there and then our shaft work term as well. Right, so this is a Bernoulli equation. We have the friction term, we have the shaft work term. Now, work done by the pump is work that is done on the system. So that becomes negative for the convention we use in fluid, right? It becomes negative. So the 155.4 here becomes negative 155.4 joules per kilogram. That's for the that's for the WS, right? And then we know that minus WS is equal to the efficiency times the work that is done by the pump. So if my efficiency times the power work is equal to minus WS, I need to be minus this value because you said WS is minus 155.4. So it will be minus of that value, right? So whatever value I get, I can put that value back into this expression. I can put it back into this expression up here. Is that okay? So what I'm just trying to say is that this is the expression we have. We want to get this term up here. Right. But then we know that it's equal to minus WS. And the WS, we said that because it is work that we're being done on the system, we are going to use negative. So it's negative of negative 155.4. Right. Then if we get that expression, we can place it into the equation. So we can also go further and then we can make HF the subject. If we make HF the subject, we get the equation in this form. Right. So we can make HF the subject in the first equation we see up here. And it will give us the equation in this form. Now, we can also group the terms. So the pressure terms can come together to give us what we see here. The elevation terms can come together to give us what we see here. Then the velocity terms from the kinetic energy can come together to give us this. And then we have the work from the pump, right? So that becomes our expression. Then we can simplify and then put in the values. So we know the inlet pressure, we know the outlet pressure. We can put in their values. We know the density, we know the value of acceleration due to gravity. We also know our Z1. We took it to be our reference, so that's a 0. Then our Z2, we said was 3.05 away from Z1. V1 and V2, we concluded that they were the same, right? Because we concluded that over here, that V1 and V2 are the same. Sorry, so we concluded that V1 and V2 are the same. So this term can go away, and then we'll have this left. Now, sorry, a minute. Okay, so we can carry on. So we have our HF to be equal to all of this now. And we know our values Z1, Z2, P1, P2. We can just put all the expressions in our equation. Then, as we said, V1 and V2 are the same. So I can change the V2 here to V1. And I have V1 squared minus V1 squared. So that can go to 0. And I'm left with this expression. But then before we continue with the simplification, realize something that's in the question. The pressure was given in kilo Newton per meter squared, right? But then every other thing was given in joule per something. So if we look at it, yes, they work from the pump. So I think I can even work with this slide. So if you look at it, the work from the pump was joule per kilogram. But here we're having kilo Newton per meter squared. It means that if you're working with kilo Newton, then it means you're going to be having kilo joule coming in there. But then every other term is in joule, right? So we have to multiply the pressure part by 1,000 so that it's also going to be in joule, no longer kilojoule. Otherwise, our units are not consistent. We can't add kilojoule to joule. We have to change the kilojoule to joule before we add them, right? So that's why we multiply by 1,000 over here. Now we worked the solution out in the head form where we divided everything by gravity, the Bernoulli equation. So I want you guys to try it out later in the other form, right? And this is the answer you should be expecting. So when you are free, you can try it out. You should be getting the same answer, right? Just for the sake of practice. Okay. So that is it for the mechanical energy balance. And we'll move to momentum balance. But before I carry on, are there any questions? Are there any questions? Okay, then. So we can carry on with momentum balance. So we have the overall momentum balance, just the same way we have the overall mass and an overall energy balance, right? When we look at the overall momentum balance, we use it for analyzing forces that are involved in fluid systems. So the quantity that characterizes the motion of a body is the momentum, right? That property that we use to define the motion of a body is its momentum. And we know that momentum is just mass times velocity, right? So that's its unit, and it's a vector quantity. Well, for what we are looking at, we're only going to consider linear momentum, not angular momentum, right? Yes. Then the momentum per unit volume is rho times v. And if you think about it, it makes sense because we say momentum is mass times velocity. If it is per unit volume, then I'm dividing by volume. So that's my capital V. Mass over volume is giving me the density there. So that's where it's coming from. Now, Newton's second law states that the time rate of change of momentum of the body is equal to the sum of all forces acting on the body and takes place in the direction of the force. So that's the second law in mathematical terms, right? This is where we get F is equal to ma from, that expression, right? So this is Newton's second law in mathematical terms. And this is what we are going to work with for our momentum balance. Now we are seeing here that the overall momentum balance for, the overall balance for momentum is very similar to that for mass and for energy, right? So we can have the sum of forces that are acting on the control volume. So equals the rate of momentum out minus the rate of momentum in plus the rate of momentum that gets accumulated in the control volume. So we earlier made mention of this relation, and the sum of the forces is a vector sum because force is a vector, right? And remember our vectors, how we add vectors, how we subtract vectors. Those things are very important for this part of the course. So we can find the sum of the forces in the x, the y, and then the z direction, right? When we are dealing with vectors, we can find the sum of forces in the x direction, the sum of forces in the y direction, in the z direction, then we add all of them together. So our sum of forces is going to be all our forces in the x, the y, and then the z direction. Then the forces that we are going to consider, we can classify them as several kinds of forces. So we'll talk about the various kinds of forces that we can expect in our system when we are dealing with fluid transport. But before we do that consideration, we only want to consider forces in the x direction for now, right? So for the meantime, we're just looking at forces in the x direction. We don't want to consider the y and the z for now. So we have different kinds of forces that we consider when we are doing this kind of analysis. The first one is called the body force. So the body force, we represent it with F subscript xg. The x is talking about the direction. The g is talking about the kind of force you're looking at, right? So it's the x-directed force caused by gravity acting on the total mass in the control volume. Or basically what we are saying is that it's the force that comes about because of the effect of gravity, right? So Fxg is just going to be mass times the acceleration due to gravity in the x direction, right? But then Fxg is going to be zero if the x direction is horizontal. So I know that acceleration due to gravity acts downward. If I'm looking at my analysis in the x direction, right, I'm not going to assume that there's going to be an acceleration due to gravity component in the x direction. So Gx is zero. This is the component of the acceleration due to gravity in the x direction. It is zero, right? So there is no body force in the x direction. Okay, there's no body force in the x direction. If it was in the y direction, then we can have some body force there, right? But even about this, I'll say something later on. I'll make mention of something later on. Now we also have what we call the pressure force. So like that for body force, because it deals with acceleration due to gravity, you see the G subscript here. So I said that the first one is giving you the direction. Then the next subscript tells you the kind of force you're dealing with. So Fxg is the body force acting in the x direction. Fxp is the pressure force acting in the x direction. So this is the x directed force caused by the pressure acting on the surface of the control volume. So when the control volume passes through the fluid, the pressure is taken to be directed inward, perpendicular to the surface, and the appropriate components must be considered. What we are trying to say is that if I have a pipe, right, and my control volume is all around the pipe, the control surface is going to be the boundary of it. So we are saying that if the control surface will pass through the fluid, so the fluid actually passes through this point, what's going to happen is that the pressure effects, I'm going to direct it inward and perpendicular to that surface. So I have a certain cross-sectional area here. I'm going to take my pressure to be acting in this direction. In the same way, if I have a certain cross-sectional area here, I'm expecting my pressure to be acting in this direction. That's the convention we use, right? But you see an example where the one outside looks like it's coming this way, right? So I think when we get to the example, I would come back to this point and I'll make mention of something. So I'll talk about the body force and the pressure force again with an example so that you get the little points that we are highlighting. Now, they're also saying that if part of the control surface is solid, I think there's a question. Good. So someone is asking that since the acceleration due to gravity acts vertically downward, how does it result to a force in the x direction? It doesn't. That's why we are saying it goes to zero, right? So because it doesn't have an x component, an x direction component, then it goes to zero. So Fxg is zero. The body force in the x direction is zero. Remember we said we are just considering the x direction for now. If we're considering the y direction, then it would have a value. Is that okay? Okay. So if part of the control surface is solid and the wall is included inside the control surface, there's a contribution to Fxp from the pressure on the outside of the wall, which is typically atmospheric pressure. What we are saying by this is, if we should take our boundary of our system and there's a solid wall there, right? We don't just consider the pressure coming from the fluid, we consider the pressure from the atmosphere as well, affecting that system. So this is what I'm trying to say. If I have a pipe flowing this way, or I have a pipe this way, and I have fluid flowing through this direction, right? What we are trying to say is that the pressure effects, you're just going to consider what's happening with the fluid. The atmospheric pressure will be catered for in there. So I can look at the effects of pressure on the fluid. And then if I have a point where maybe there's a solid component, so the fluid is coming in this way, but then this side is sealed, right? There's going to be an effect of the fluid causing some kind of pressure here, but there's also going to be atmospheric pressure from outside that I have to account for. So when we have a solid component included in our control surface, we need to also consider atmospheric pressure, right? Now, the other kind of force we have drag force, which is also friction or shear force. And we can integrate this over the x direction to get the entire frictional force of our system, right? So it is exerted on the fluid by a solid wall, and the control surface comes between the fluid and the solid wall. What you're just trying to say is that this is the force that comes about because of the friction effect between the fluid and then the wall. And this force is parallel to the fluid flow, and the appropriate components must be considered for areas not directed along the x-axis. In many cases, we can neglect this force. So usually, if you are been given a question and nothing has been stated about the drag or friction force, you can assume it's negligible, right? And then if we are working with it, we need to consider the appropriate components. In fact, for all the forces, we have to consider the appropriate components. Because if you are working in the x direction, we have to resolve our forces in the x component and work with that, right? If we are working in the y direction, then we resolve in the with the y component and then work with that. Okay. Yeah. So you can also have a solid surface force Rx. You can have what we call a solid surface force Rx. This is the S component of the resultant of the forces acting on the control volume. As this is where the control surface will cut through a solid, right? So this is just looking at the reactive force of the solid on the fluid or the fluid on the solid. I think my network is down. Hello. Okay. So the solid surface force is just looking at the effects of the force of the, so is the force that we see when the solid is acting on the fluid or the fluid is acting on the solid. There's some kind of reactive force. So you know that if let's say I have maybe a flat surface and I have a block on the surface, right? There's a way that the block is going to exert downwards. Sorry, there's a way that the block is going to exert downwards. But there's also going to be some reactive force from the ground to support the block. And all we are just trying to say is that if I have fluid moving through a system, there's some reactive force that um the solid part of the pipe is acting is there's an effect that it's having on the fluid. And then the fluid is also going to have some kind of reactive force on the solid surface as well. Right. Okay. So this one is just the effects of the solid on the fluid or the fluid on the solid, depending on the direction you want to come from. So this occurs typically when the control volume includes a section of pipe and then the fluid that it contains. So remember we said that the sum of the forces should be equal to the change in momentum with time. If we consider just the x direction, then we'll have the body force in the x direction plus the pressure force in the x direction plus the shear force plus the surface force to be equal to the change in momentum. So that's momentum out minus momentum in over time. So momentum out is going to be m2 times v2. That's for the outlet. And then in it's m1 times v1. Because it's divided by time, then the mass becomes mass flow rate. That's why we see the m with the dot on top now. So please take note of this expression. Now, remember we said that when we are solving equations that have to do with balance, mass, energy, or momentum, right? There are some things we need to consider. So remember we said that we need to first locate and specify a coordinate system origin. So I spoke about this the last time. We need to define our origin, where we are starting from. Then we need to choose our coordinate system that will match the characteristics of the system. Then we specify the flow region and then we make a sketch of the problem. The reason why I'm emphasizing this is because we are dealing with forces and the kind of coordinate system we use matters. So I think you should have come across this in basic mechanics. Someone might do the analysis and they might say that this is their x axis and then this is their y axis, right? Another person might do the same analysis and say that this is now going to be their y axis and this is going to be their x axis. Irrespective of what you choose, you just need to make sure that you are consistent with your calculations. So it means that the person who uses the x-axis in this situation, right? If he is comparing his answers to the person who used the y-axis, you need to make sure that they are still doing the same thing. So for this person, the body force in the y direction will rather be zero, right? Because gravity doesn't work in this direction. Gravity works in the vertical direction, not in the horizontal direction. Is that okay? So whatever system you specify, make sure it's consistent. And this is very important because once again, someone might consider this system over here, right? Another person might say that this is going to be their x direction. but then their y direction is going to point downwards instead. So this is going to be their y direction. Whatever system they choose, they need to make sure that their units are consistent. For the first person, if you are using this to be your y direction, you know that acceleration due to gravity acts downwards. So the components or the acceleration due to gravity, right, in the y direction is going to be a negative value for that person. Because it's supposed to act downwards, but you're taking your y to go upwards. For the other person, the acceleration due to gravity is going to be positive because he's taking his y to be going downwards and it's moving in the same direction as the acceleration due to gravity. So all that I'm trying to say over here is that you need to choose your coordinates very carefully and then the directions they are going in because you're working with vectors. And for vectors, you're not just interested in their magnitude, you're interested in their direction as well, right? So that being said, let's look at an example. Now, this is okay, I think I have to. Okay, yeah. So this is our system, right? And what we are saying is that what was I was saying earlier about the coordinate system is what we see here. So usually they define that system. When we are dealing with momentum balance, you need to draw the axis to indicate what you are taking as your x-axis and what you are taking as your y-axis. Right. So you need to define what you are taking as your x-axis and what you are taking as your y-axis. Then the other thing we're talking about was the pressure acting inward and perpendicular. What I'm trying to say is that if I have the fluid flowing in this direction, as this surface here, I'm expecting the pressure to act in this way. But then at the outlet here, I'm expecting the pressure to act in this way. So it's supposed to act inward and perpendicular to the surface. But we realize that when we do our analysis, we consider the pressure rather acting this way. It means that the pressure that is coming out, I'm going to negate it so that it moves in the opposite direction. Because I'm working with it this way, but I need it to be in the opposite direction. So you get to a point where you see P1, right, times A1 minus P2 times A2. The minus is coming from this part here. The fact that we expect it to act inwardly, but it's acting outwardly, right? So that's all that we're trying to see from that point that I said I would reference. The fact that the pressure acts inward and perpendicular to the surface, right? Okay. Now, we can work with the following assumptions that we are dealing with steady state. So momentum is not accumulated in the system. And the flow is only working in our x direction, what we have specified as our x direction. So it means that the velocity in the system is equal to the velocity in just the x direction. And also assume that density is constant. And then all the flow inward is normal to A1. And all the flow that's coming out is also normal or perpendicular to the cross-sectional area at point 2. So we like that if we are considering just the y direction, then we can account for the effects of gravity, right? But in this case, we can't. We are considering just the x direction. So we can see the direction in which our coordinate system is being considered. So that's what we are talking about here. This is the direction in which our coordinate system is being considered. So someone could have decided to switch the y and the x. In that case, it means that the effect of gravity will be experienced in the x direction and not the y direction, right? So you can switch the y and the x. And then it means that for your case, gravity's effect will be experienced in the x and not the y direction. So for our discussion, we are just considering flow in the x direction and there's no effect of gravity. So the body force in the x direction, as we said earlier, can be taken to 0. So the body force for the inlets and then for the outlets are all going to be equal to 0. Now, if we assume that shear forces are also equal to 0, then the shear force in the inlet and then the outlet in the x direction will go to 0. Then for pressure force, we know that pressure is equal to force over area. So if I make force the subject, I'll have pressure times area. So this is our expression for pressure force. Now, FXP, that's at the inlet, it's just going to be the pressure at the inlet times the area at the inlet. And then at the outlet, it's going to be the pressure at the outlet times the area at the outlet. But remember, we expect the pressure at the outlet to move in this direction, which is opposite to the pressure at the inlet. Or even if we consider our coordinate system, right, the pressure at the inlet is moving in the same direction as our x-axis. That one is positive. And the one at the outlet is moving in the opposite direction to our x-axis. So it's the negative x direction. So if we should find the total pressure force, it becomes P1A1 minus P2A2. So that's what we are trying to see. Right. Okay. Now the solid surface force, it considers the reactive force acting on the system. So we can put the whole expression together. So this was the expression that I told us to take note of, right? And we said that the body force is gone. We are assuming there's no shear force. So we are left with the pressure force, which is this one here. Then the solid surface force, which is this. and then a change in momentum, which is what we see here, right? So we can simplify it and make Rx the subject, and this is what we get. Now, Rx is the force that the solid is going to exert on the fluid. If we want the effect of the fluid on the surface, then we have to negate it so that it's moving in the opposite direction, right? So if we are looking at the effect of the solid on the fluid, then it's the value that we get for Rx from this expression. And then if we want the effect of the fluid on the solid, then we can negate it. Now, if the conduit axis, so this is our conduit or our pipe. No, the section 2 is not closed. It's open. This section is not closed, it's open. So if we consider our conduit or our pipe to be curved and not horizontal, then we need to do a balance for the Y momentum as well. So what we are saying is that we can have a pipe that looks like this and is bent this way. So we have a curved pipe. We don't only consider the X direction, but we consider the Y direction as well. That's what we are trying to put across. Okay. So we have an example here. Water flowing at a rate of 0.03154 meter cube per second through a horizontal nozzle shown in the figure, and it discharges to the atmosphere at point 2. The nozzle is attached at the upstream end at point 1, and frictional forces are considered negligible. So the upstream inner diameter is 0.0635 meters, and then the downstream inner diameter is 0.0286 meters. Calculate the resultant force on the nozzle, and then we've been given the density of water. Okay, so now someone is asking, but how come the outlets, we are considering it to be in backward? So remember we said that when the fluid is flowing, right, we consider the pressure to be acting inwardly and perpendicular to the area we are working with. So if we are looking at this case, it has to act perpendicular to it and it has to act inwardly. So it's going in this way. If you look at the outlet, so this is for a question someone is asking, it has to act perpendicular to the surface, but it also has to act inwardly. That's the convention they use. You can take it to act outwardly. It's still fine, but it just means that you're going to do in minus out at the end of the day. It's the same understanding. So that's where it's coming from. So the points we are referring to is here. This point here. That's why I made it bold because I realized that it might become a bit controversial for some of us. So if you want, right, you can just take it that the pressure is acting outwardly. And at the end of the day, you're just going to do the pressure force in minus the pressure force out. You get the same thing. You still get your P1A1 minus your P2A2. You still end up with this expression here. If you do it, your pressure force is equal to the pressure force in minus the pressure force out. Your in minus out, you get the same expression. Is that okay? I was just trying to explain what that point meant from the reference material. Okay. So this is the question that we are dealing with. We've been given the um, diameter of the inlets and the outlets, and we'll be given the volumetric flow rate through our system, and then we'll be given the density of water. Now we'll start with our momentum balance expression. And what we need is the mass flow rate, and then the velocities. All we have is just the volumetric flow rate as the inlet. So we work with that, right? Work with what we have to get what we don't have. So if we consider that, we know that density is equal to our mass flow over our volumetric flow, which are represented with Q. So it means that our mass flow is just density times our volumetric flow. We had the density of water to be 1,000 kilogram per meter cube. And the volumetric flow from the question was 0.03154 meter cube per second. So I can multiply them and then get the mass flow. I remember we said that for such systems, the mass flow at the inlet is equal to the mass flow at the outlet. So M1 is equal to M2. Now we can find the velocities as well. We know our volumetric flow is also equal to our area times our velocity. So we've proven this several times. If I make velocity the subject, I'll have the volumetric flow divided by the area. So our volumetric flow at the inlet, sorry, our velocity at the inlet is going to be the volumetric flow at the inlet divided by the area at the inlet. That's just going to be Q over pi d1 squared over 4. This is the area at the inlet. If I put the values in, this is what I'll get for the velocity at the inlet. I can do the same thing for the velocity at the outlet using the area within the diameter at the outlet. So now I have my velocities, I have my mass flow. Now, since our conduit is horizontal, we are only considering flow in the x direction. We can assume that there is no effect of gravity in that direction. So our body force is zero. And if we also assume that our shear force is negligible, Fxs goes to zero. So we have a general expression. We can cancel out the terms that have to be cancelled out. Then we can take it from there. So we know our mass flow and our velocities now, right? We've taken our body force and then our shear force to be zero. So we are left with this expression. Now we need to find our pressure force and we require pressure and area. But we have the diameter at the inlet and outlet, so we can find the area. We don't have anything, or no, let me not say that way. We don't directly have the values for the pressure, right? So what do we think we can do from what we've done so far? Mass energy balance. What do we think we can do to find the pressure? I want someone to give an answer to that. What do we think we can do to find the pressure? Anyone? So if we consider our mechanical energy balance, what we did yesterday, the Bernoulli equation, we can use that to find the pressure, right? So we need pressure in area to get the pressure force, but we don't know the inlet pressure. We know the outlet pressure, yes, because we were told it was um, atmospheric from the question. So we know the outlet pressure. So we can use Bernoulli's equation to find our inlet pressure, right? So this was the Bernoulli equation. And then we also assume that there's no change in elevation. So this can go to zero from the Bernoulli equation. We assume that there is no shaft work, so this can go to zero, and that there are no frictional losses, so this can go to zero. Right. So all that we are looking at is the pressure and then the velocity terms. We are looking for P1. So I can have this expression and then make P1 the subject. Right. So I can simplify this or expand it, make P1 the subject, and then I'll get P1 to be equal to this value. Right. The atmospheric pressure, we were using 101325 Pascal. Right, so that the units can be consistent. So when we are done, we are going to end up with this expression over here. We are going to end up with this value for P1. So now that we know our pressure at the inlet, you can find the pressure force. We know the pressure at the outlet, you can find the pressure force there. So it's just going to be the pressure at the inlet times the area at the inlet minus the pressure at the outlet times the area at the outlet. So that's going to give us this value we have down here. So please always write your units there. Should be in Newton. So this was the expression we simplified this to. We can make Rx the subject. Now we have our values for our change in momentum and then our pressure force. If I put the values in there, it gives me this answer. Right. So try it out and then confirm the answers. Right. Just in case I made a mistake with the calculation. I think I checked it again, but then confirm the answers. So since the force is negative, so remember we said Rx is the force exerted by the solid on the fluid or the solid boundary on the fluid. Now, since it is negative, it means that the force is actually moving from the fluid onto the solid. It means that the liquid is rather exerting a kind of force on the solid. So since the force is negative, it is actually in a negative x direction or to the left. So this is the force of the nozzle on the fluid. The force of the fluid on the solid is rather going to be given by this value instead. Okay, now this is the last thing that would be handling today. So before I carry on with this, are there any questions up to this point? Are there any questions? Okay, now what we looked at was just momentum balance in one direction, the x direction. We can consider it in two directions. So we see a certain system here. A pipe is not horizontal, it's not vertical, it's inclined. It means that it has a horizontal and a vertical component. So we'll do our balance for the x direction and we'll do our balance for the y direction as well, right? You see a certain angle here, that's gamma 1, and another angle here, that's gamma 2, right? Now, we can consider a flow system with fluid entering at point 1 and leaving at point 2. So we can make the following assumptions: still steady state flow, frictional force is negligible, turbulent flow, and we want a balance in both the x and in the y direction. So there's a need to resolve in those directions. So this was our general form when we're considering just the x direction, right? And then we said in the x direction, there's no body force, so there's no frictional, so there's no force because of gravity. And we already assume that there are no frictional forces. So this is going to be our final form in the x direction. But then we realize that pressure and velocity are acting in a certain direction that has to be resolved in the x direction. Right. So what we are saying is that the velocity that is coming in here is not coming in the x direction, it's inclined. So the V2 and V1 here, we need their x components. In the same way, the pressure force we are having, the force is not just acting in the x direction, it's inclined. So we need the pressure force in the x direction, the x component of it. So what we can do is that you know that if I have a system like this and I want to get the x component, I can have the value cos of the angle to give me the answer. So I'll have here, instead of V2, I'll use V2 cos gamma 2. That's at the outlet. So V2, right, cos the angle there. And then for the inlet, it will be V1 cos gamma 1. And then for the pressure force, it's going to be the pressure times the area at the inlet, then times cos gamma 1, and then cos gamma 2. Is that okay? So that's minus fxp. Remember, fxp was p1a1 minus p2a2. We just resolved it in the x direction. So this negative here can multiply through. Then we have the final expression as we see down here. Now, in the y direction, we can expect something similar, but this time, we need to consider the effect of gravity because for our system, gravity will be acting in the y direction. So Fyg is going to be minus mg. And that's what we're seeing the last time. It's negative because the force effect by gravity acts downward. Looking at our direction of the coordinates, it's going to be negative. So our coordinates is saying that y is acting up. The positive y direction is upward. But our gravity effect is downward. So it means it's the negative y direction. That's why we have a minus mg in there. So if our fluid was going to be flowing downward, then the y direction will be pointing downward, when our Fyg can be positive. So maybe our fluid was rather flowing down. We have said that this is going to be our y, and this is going to be our x. If we had done it this way, because the gravity is acting in the same direction as our y-axis, we would have thought it's positive. Is that okay? So now, instead of we to cancel out Fyg, we keep it in there. So we can send everything over the equal to sign to get our Ry, right? And we said Fyg is minus mg. So if we should put everything inside, this is going to be just like what we did for the x direction. The only difference now is this part here. It's going to be minus of minus mg. So I don't know that we are going to have the expression in this form. Now, failing to keep a consistent sign, sorry, failing to keep a consistent sign convention is the most common source of problems when applying the momentum balance equation. The most common thing that causes us to get wrong answers when dealing with the momentum balance is we using negative when we are supposed to use positive, or positive when we are supposed to use negative. It means we are not moving in the correct directions we are supposed to, or we made a mistake with the directions we were using. Remember, we are dealing with vectors. So with vectors, the directions are very important. Is that okay? Now, the last thing is that, sorry, if you are working in gauge pressure, then you only need to show the pressure force on the part of the boundary of the control volume, where the pressure is different from atmospheric. If you are working with gauge pressure, you just need to consider the parts where the pressure is not atmospheric. Because with gauge pressure, if there's atmospheric pressure anywhere, it goes to zero. Is that okay? Okay, so I think that is it for today's discussion. We've finished with fluid transport. Are there any questions up to this point? Any questions from where we started up to where we ended? We'll give you an assignment to try on something like this, where would have a combination of mass, energy, and momentum balance, right? But then up to this point, are there any questions? Any questions? Okay, if there are no questions, I'll send you guys the link right now, and then we can call it a day. So I'll send you the assignments. We'll put an assignment together and I would make it available to you. Okay, so that's the link. You can quickly fill it and then it will be done.